Good morning, everybody. At least it's morning for me. May not be morning for y'all. We're going to start our unit on applications of integration, and where we're going to start is how to calculate the area between two curves. And it's going to be a pretty neat lesson because we're actually going to learn how to do it in terms of x, which is what you guys are used to. Here's the formula right here. And we're also going to talk about it in terms of y. So we're going to be calculating area with respect to the y-axis, which we haven't done before. It's really neat. So let's talk about this formula right here. So how to calculate the area between two curves. This is what you're going to do. I have some pictures here I thought might be helpful. So this, if you see this picture right here, this would represent the area between those two curves. So let's see how we can build that area from the area below f of x, which would be this area right here in this picture, and then the area below g of x, which would be the area in this picture, if you can see the red. So if we look at just the area below f of x, it gives us both the area below f of x and the area below g of x, all the way down to the x-axis. So if we were to take this area and cut out the area below g of x, you can see I'm erasing it right now, then we would get the area between the two curves. So how it works is that we are just going to find what I call the top function. And every time you want to find the area between two curves, it's always really important that you determine which function is vertically on top. And so we're going to take that function, we're going to integrate it, and then we're going to subtract what I would call the bottom function. And in this case, that would be the g of x. The g of x is going to be our bottom, and then the f of x is going to be our top. So it's a pretty simple method. It can kind of trip you up if the integrals may do something, or the functions may do something like this. So say we have this, and say we're asked for the area enclosed by the two curves. Then in this case, we actually have two pieces of area enclosed by the two curves, if you can see those two pieces. And so they actually, in this case, split at this intersection between which function is on top and which function is on bottom. So say the curve is f of x, and then the linear function is g of x. So in this case, how you'd want to do this is you would actually want to break it into two kind of separate problems. The first problem would be this area right here that I've circled. And in this case, the curve is on top. So we would do, the curve is f of x. See if I can find some room to write. So we would do, for the green one, the integral from, say, a to c, make that middle value c, of f of x dx minus the integral from a to c of g of x dx. And then for the second piece, where now the linear function's on top, I'll do that one in, say, blue, we're actually going to switch it. So say this intersection point right here, we'll call it B. And so what we would want to do to determine that area is we would take and then do the integral from c to b of g of x dx minus c to b f of x dx. And then we would take both of these integrals, this one and then the one I just erased, and we would add those two areas together, and that would give us the total area. So I've given you guys some kind of helpful hints at the bottom. I say you always want to start by sketching a graph, or if you aren't given a graph. And then, if necessary, where the two graphs intersect. In some cases, you're given the error bounds, kind of like in this picture example that I've shown you. And then in some cases, you're just asked for the area enclosed by the two graphs. So if you're just asked for area enclosed, then you have to find the intersection points where the two graphs intersect. And then you also have to check if they cross somewhere in the middle and the top function and the bottom function get flipped, like this example that I've just shown you. Then you want to determine the function of intersection. If it's a calculator problem, you can use your calculator. If it's a non-calculator problem, you can just set the two functions equal to each other and solve. And then once you get done with that, you're going to set up your integrals. You're going to evaluate. So let's try an example. So here I'm given a picture, so that's nice. And I want to find the area of the region enclosed by these two graphs. The curve obviously is x squared plus 2, and then the linear function is 2x plus 5. And I can see by the graph, it seems that they intersect at 3 and -1. So these are going to be my limits of integration. And then I look at my functions, and I see the blue function is my top function. Oh, sorry. And the pink function's my bottom function. So the linear function is going to be the one I put on top, and then my x squared plus 2 is going to be the one that's on bottom. So let's go ahead and set up our integral. So we're going to do the integral from my bounds are -1 to 3. My top function is the linear piece, so that's going to be 2x plus 5 dx. And then I'm going to subtract the area under that curve. The curve, the x squared plus 2. So that's going to be the integral from -1 to 3, x squared plus 2 dx. And then I just evaluate each one. If I weren't given a picture, I could pretty easily set these two functions equal to each other and solve for x. So let's see here. If I integrate this, I'm going to get 1/2 times 2 times x squared, so that's going to be x squared plus 5x. I usually do these completely separately just so I don't have to deal with the negative signs as much. I can just subtract in the end. Minus, this one's going to be 1/3 x cubed plus 2x from -1 to 3. And then whenever I plug everything in and I evaluate, let's see, this on the left I get 9 minus, and then the one on the right I get -5/3 minus -5/3. And so whenever I combine those two together, I get 32/3 is my area. And so now this is the area enclosed by the region between those two curves. It's pretty simple. So let's try one that gets to become a little more complicated. So they ask us first to sketch the region and then compute the area. And they say along the x or y axis. So obviously this is going to be along the x-axis because my independent variable for both of these is x. They're both solved for y. But we are going to do one with the y-axis in just a second. Okay, so I'm going to draw the picture first. I would say in most cases these would be calculator problems. And so although you're required to sketch a picture, I would graph the two functions on my calculator. So they intersect at -2 and +2, and as well as the y-axis where x is 0. And so it's going to look something like this. It just needs to be a sketch. So I've got that piece. And then my curve, my x all or over x squared plus 1 looks a little bit like this. So this area right here is the area that I'm interested in. I had to zoom in a little on my calculator in order to see things clearly because there's not a lot of distance between the two functions. All right, so now I can kind of see my bounds. I know that it's gonna be split up into two parts because I can see that my linear function x over 5 is on top from -2 to 0. So sometimes I'll make myself little notes. And I'll say, okay, from -2 to 0, x over 5 is on top. So I know that's going to be the first function in my integral. And then from 0 to 2, x over x squared plus 1 is on top. So I'm going to end up with 4 integrals altogether. And so I'm going to take this and I'm going to work it as two separate problems. The first one being from -2 to 0, the next being from 0 to 2, and then I'm going to add those two areas together. So let's do the area on the left first. So my linear function's on top, so I'm going to do x over 5 dx, and then I'm going to subtract the integral from negative 2 to 0 of x over x squared plus 1 dx. Now, a lot of times these will be calculator problems, so you really just have to set the integral up, and then you can use Math 9 on your calculator to evaluate it. I am going to show you the antiderivative, just in case you were wondering. So the antiderivative of x over 5 is going to be x squared over 10. So I'm going to evaluate that from negative 2 to 0. And then I'm going to subtract. This second one's a little more complicated. I'm actually going to have to use a u sub, and I would let my u equal x squared plus 1, and then my du is equal to 2x dx. And I'm going to kind of skip a lot of steps, and I'm not going to change my limits of integration, but I know it's going to happen as I'm going to get 1/2 the natural log of x squared plus 1. So I'm actually going to plug back in. And this is going to go from negative 2 to 0. So now I want to evaluate each one independently and then subtract. So if I evaluate the left piece, I end up with 4 over 10. And then when I evaluate the right piece in exact form, I get 1/2 times the natural log of 5. And then I could approximate this. I will in just a second, though. So now let's look at the other piece. So let's take a look at the integral from 0 to 2. So now my curve is on top to the right of the x-axis. Then so I'm going to do x over x squared plus 1 first, dx. And then I'm going to subtract the linear function because that's on the bottom. So 0 to 2, x over 5 dx. And I already know what my antiderivatives are. So this one, is going to be 1/2 the natural log of 5, right? And then this one's going to be 4 over 10. And then if you'll notice, these two pieces are kind of opposites. I have a positive 4 over 10 and a negative 4 over 10, a negative 1/2 ln 5, and a positive 1/2 ln 5. So when I combine the two, I actually get 0. I'm going to pause this for just 1 second, and I'll be back. I want to check on something, and then I'll give you guys the final answer. Well, I'm glad that I took that little break because I found a mistake that I made. It seems, though, that this actually should be a negative 4/10. Maybe you guys caught that because I'm going to do 0 minus 4 over 10. And then this over here should actually also be negative because that's going to be 0 minus 1/2 ln 5. I knew that my signs weren't working out and I shouldn't get 0. So then, nice enough, when I combine these two together, I end up with 2 negative 4/10. So that's going to be a negative 8 over 10. So I'll write that as a negative 4/5. Oh, let's write it like this so I make a nice math statement. So I'm going to have 1/2 ln of 5 plus 1/2 ln of 5 minus 4 over 10 minus 4 over 10. And then this is going to be equal to just ln 5 minus 4/5. So, and that's going to be the area enclosed by the two curves. So I told you guys that we are going to find out how to integrate and find area with respect to y. So let's take a look at this example over here in this formula. So it's really interesting, especially drawing the graphs. You kind of have to take your mind and twist it just a little bit in order to see what's happening with the graphs. So here's our formula. So how it works, say I am integrating sine A, or I'm writing x is equal to sine y, and I want to draw this graph. Then I know that sine x, looks something like that, close to 0. But I almost what you have to do is you have to rotate it and twist it in order to look at what happens with the y-axis. So I have to think a lot of times in terms of where is positive and where is negative. So let me redraw this. That would have been with respect to the x-axis. Let's draw it with respect to the y-axis. Well, I know that my positive part for sine is above the y-axis, so I think that my curve is going to fall like that. And then my negative y is going to be below the y-axis. So this would be the graph of x is equal to sine y. It's pretty difficult to sketch the graphs without a calculator, and even then, you have to graph in your calculator with respect to x. So you kind of have to take the function and twist it around. You really just need to practice this. Right, so let's look at the formula before we try to graph our two functions. So instead of thinking top bottom, you have to think left right, or right left actually. So I really like the way that this is written, how they have x on the right minus the x on the left. So you're going to look at your two functions, you're going to see which one is the function is the farthest to the right, and that's going to be the one that quote unquote goes on top. That's going to be the first function when you subtract. And then the one that's more to the left is going to be the second function. So let's take a look at these graphs right here, or these functions. So I have one that's already solved for x for me. It's y cubed minus 18y. But then this one is not solved for x or y. It's set equal to 0. So since this function right here, I can't solve for y, there's no way I could isolate it, I'm going to have to take this one and solve it for x. And then I'm going to integrate both of them with respect to y. So this is going to become, if I solve for x, negative x is equal to negative 1/2 y. And then, of course, I have my other one. So let's work on the graph first. So if you were to look at this graph on your calculator, you would probably see something that looked like this. I think that's a pretty decent sketch. So what I see here is I see that when my values are negative, because now I'm looking at it in terms of x, that my curved portion is on top and my linear portion is on the bottom. And when the values are positive, my curved portion's on the bottom and my linear portion's on top. So now what I want to do is I want to try to rewrite this and think instead of terms of positive x and negative x, in terms of positive y and negative y. So this is what's going to happen. So my linear piece is going to be on the top when y is positive. So I think that it's going to be above the y-axis, sorry, to the right of the y-axis there. And so my curved piece, when x was positive, my curved piece was on the bottom. So when y is positive, my curved piece is going to be on the bottom. And I think it should look something like this. So now we're looking for this area right there, and that area right there. And if you're using Math 9 on your calculator, as long as you can visually see which functions are on top and which functions are on bottom, sorry, keep doing that, which functions to the right and which is to the left, you can still use Math 9 and just integrate with respect to x. It's not going to change anything. So now I'm going to set up my integrals. So you can see I'm going to have to split this into two pieces I'm going to add together. So for this piece right here, negative 1/2, y is on top. Sorry, is on to the right. For this piece down here, my y cubed minus 18y is to the right. So let's set up these two. Let's see. So my first one, oh, okay, also didn't do this. I didn't find their point of intersection. So you could have done this on the calculator and just used the intersect function. But if you set these two equal to each other, y cubed minus 18y is equal to negative 1/2 y. then what you end up with is you end up with y cubed minus, sorry about that, 17.5y is equal to 0. So I do get that y is equal to 0, which makes a lot of sense in the graph. And then I get that y squared is equal to 17.5, which is kind of strange. So I just approximated that with the decimal because I knew it wouldn't be a very nice number. So I'm going to get that y is equal to plus minus 4.183. So I actually did use decimals in this. I guess you could have done the square root of, 5 over 2 or whatever it would be, but this will be a little easier. So I know that my lower limit is going to be negative 4.183, and then it splits at 0 in the left and right flip, so we're going to go to 0. And then remember, when y is positive, my linear function's on top, so this is going to be negative 1/2 y. And then we're integrating with respect to y, so we put a dy there. And then I'm going to subtract the integral from negative 4.183 to 0, and now this is my curve, y cubed minus 8y dy. Alright, so when I integrate these, you take the antiderivative just like you would with respect to x. So here I'm going to end up with this will be negative 1/4 y squared minus 1/4, oh, we're going to do these separately, sorry, from negative 4.183 to 0, and then I'll move down here so I have a little more room. And then the next piece was y cubed minus 18y, so when I take that antiderivative, I'm going to get 1/4 y to the 4th minus 9y squared, and then I'm evaluating this from negative 4.183 to 0. And whenever I do all the math and plug everything in, I get 76.562. And the pieces look fairly symmetric. So my guess looking at the graph is that that second piece of area is also going to have the same value, but we're going to see. So now if I look over here at my graph, I see that when y is negative, or below 0, y equals 0. Oh, I think I flipped that around and did it backwards. Golly. Geez, I'm driving you all crazy with all the mistakes this morning. I think it's a little too early for me. So what I'm going to do is, since this is where y is negative, it's sometimes really hard to think in terms of y negative and y positive. I'm just going to change these limits of integration. And we're going to look at the positive piece first. So since this piece, let me show you guys my mistake, maybe you can learn from it, is above the y-axis, then this is going to be where y is positive. So this is actually going to go from y equals 0 to y equal 4.183. And that would be that value right there where the two intersect. And then where the curve is to the right, this is going to be negative 4.183 to 0. So what I can do is I can just change these and do 0 to 4.183 and then 0 to 4.183. And then pretend like the rest of them were changed also. I guess I could do that. And so I'll fix this. It'll be 0 to 4.183 and then 0 to 4.183. So now, and you actually do get the same area for both, I already know, so I don't have to change my answer, but it's a good lesson to pay attention to when y is positive and when y is negative. It's really hard to think in terms of y sometimes. So now for the negative piece, which is going to be the one below the y-axis, the x-axis, sorry, this piece right here, then our curve is on top. So this is going to be, it's the negative piece. So it's going to be the integral from negative 4.183 to 0. And then my curve is to the right. So this is going to be y cubed minus 18y dy. Oh, forgot my dy there. Too early for me to be doing all this. Now we're going to subtract the linear. So that's going to be negative 4.183 to 0 of 1/2 negative 1/2 y dy. And you guys have already seen the antiderivatives of both of these, so I'm just going to plug in for you and show you that you end up with the exact same area that you found before, which was 76.562. And then if I take these two and I add them together, my first area was 76.562. My second area was 76.562. And then when I combine both of these, I get 153.125. So that would be my total area between those two curves. And that's a lot of work. So that would be, this total area right there. All right, well, I hope you guys have learned something about finding the area between two curves. I definitely think that you're going to need some practice doing it with respect to y, but this will really come in handy whenever we start doing volumes of solids of revolution, because there you really have to, sometimes you have to integrate with respect to y. All right, well, you guys have a great day.